Okay, students, welcome to the second and concluding part of Chapter 7's coverage of electron delocalization. After this lecture, you should be able to explain how resonance affects acidity, identify the products of adding HX and X2 to conjugated dienes, and predict which products would be favored under thermodynamic versus kinetic conditions. Predict the products of Diels-Alder reactions with proper stereochemistry shown, and explain why that product and stereochemistry are favored. And please note that we will skip section 7.8. Alright, so I want you to imagine that I ask you this question. Draw the different resonance contributors or resonance structures of sulfate shown here. I'm not going to do that, but I only wish to mention that you should, from our previous lectures, have the knowledge necessary to do that. Here's the real question. Why in the world is sulfate so stable? Of course, the answer is because of all of its resonance structures. That negative charge on this oxygen shown here is not localized to that oxygen, but is in fact delocalized and shared by all three of those resonating oxygens. So, what does this tell us about sulfuric acid, H2SO4? Well, as you'll note, this molecule, sulfate, is the conjugate base of H2SO4. In other words, if you put a proton on sulfate, that is, replace the negative charge on sulfate with a hydrogen, you get to H2SO4. Well, guess what? H2SO4 is one of the 7 strong acids I ask you guys to memorize in general and organic chemistry. It is, in fact, one of the strongest of the strong acids. So this brings us to the $60,000 question. How does electron delocalization or resonance affect a compound's acidity? Well, I hope you can see that the more stable the conjugate base, the stronger the acid. So in other words, if you've got a conjugate base that has lots of stabilization by resonance, chances are the acid from which it came is going to be very strong. And in general, that principle will hold true. The more resonance and the more stabilization we see in our base, the stronger the acid from whence it came. So what are our take-home lessons from this section? The more stable the conjugate base, the more acidic the acid it came from. The better a conjugate base can handle a negative charge, the more stable it is. Resonance helps conjugate bases handle negative charges better. Therefore, more resonance in a conjugate base generally means the acid it came from is more acidic. Now I'm going to show you a slight variation of this mess housed in a new reaction. You see, if I take a conjugated diene like this one and I add HBr to it, I actually end up getting 2 products. This one and this one. How? The answer is in the mechanism. So here is that mechanism. Electrons come out of the alkene, grab this hydrogen. The hydrogen, of course, gets placed on the less substituted carbon to give me the more stable carbocation. Now, if the bromide comes in and forms a bond with this carbon, the product that I get is this one, which is the first product we see up here. However, you should remember that this carbocation intermediate can resonance delocalize. These electrons flip over. It gives me partial carbocation charge at this position. Bromide comes in here. It gives me that as my product. Hence, we end up getting both products as a mixture in this reaction. Now, one thing that I hasten to mention is that this carbon right here is not a primary carbocation. It is not. It is a primary allylic carbocation, which is much more stable. Remember that by resonance, this positive charge right here is actually being shared by 2 carbons, this one and this one. It is resonance delocalized. Hence, this carbocation actually ends up being even more stable than a tertiary carbocation. Let's try adding a halogen to our diene. As expected, when we take a diene and add a halogen such as bromine, we get 2 products, the one to the left and the one to the right. What is the mechanism? Once again, electrons come out and grab a bromine. We need to remember, however, that that bromine forms this bridged bromonium intermediate. Now what can occur here is these electrons can flip over here and open this ring up to give me the resonance stabilized carbocation at this position. If my bromide comes in here and kicks this one open, I get this product, which is the first one. If my bromide comes in there, it gives me this product, which is my second one. Now this brings us to an important point. For reactions that can potentially form two different products, like additions to dienes, we can control which product is favored as long as one is a kinetic product and the other is a thermodynamic product. So what does that mean? Let's give you some explanations followed by an example. I'll now define the kinetic product. The kinetic product is the product that forms the fastest. Kinetic products come from the most stable carbocation intermediate. Kinetic products are favored at low temperature, which we call kinetic control. You can pick out the kinetic product by choosing the product that arises from the most stable carbocation intermediate. Now, in contrast, the thermodynamic product is the product that's the most stable final product. Thermodynamic products are favored at high temperature, called thermodynamic control. You can pick out the thermodynamic product by choosing the product that is the most stable final product, regardless of which carbocation intermediate it came from. Remember this: the more carbons there are attached to a double bond, the more stable that double bond is. That's called Zaitsev's rule. So let's apply that back to our previous example. As you'll remember, in this reaction, the addition of HBr to our starting diene gives two products. Which one is the kinetic and which one is the thermodynamic? Let's re-examine the mechanism. The electrons come out and grab the H. The H goes on the less substituted carbon to give me this carbocation, which of course is resonance delocalized with this carbocation. These are both resonance contributors. Now I'm going to stop right here. Before we look at the actual products, I'm going to ask you guys the question: which of these two intermediates is more stable? I've got a secondary allylic carbocation and a primary allylic carbocation. Which one is more stable? It's, of course, the secondary allylic carbocation. Hence, because that is the more stable intermediate, the product that arises from it is the kinetic product. What this really means is that if you are running this reaction at low temperature, like negative 78 degrees Celsius, this is the product that you would get as the major product. The reason is because this more stable intermediate is the one that would be favored at low temperature because it can't go back and forth as quickly or as easily at that temperature. Does that make sense? Kinetic product always arises from the intermediate that's the more stable intermediate. So now let's see if we can figure out which one is the thermodynamic product. Remember that the thermodynamic product is the final product that is the most stable final product, irrespective of which carbocation was more stable. So what we do is we look straight at the products. I've got a product right here. It's a mono-substituted alkene. And I've got a product right here that's a di-substituted alkene. Which of these two alkenes is more stable? Remember Zaitsev's rule. The more substituted the alkene, the more stable the alkene. Hence, this is the more stable final product. At high temperature, basically any temperature that's positive in the Celsius scale, this is the product that will be formed. It is the thermodynamic product. The reason is because at those higher temperatures, this rearrangement between these two resonance structures is happening fast enough that we eventually siphon off all of the product to our thermodynamic product instead of getting a bunch going to kinetic. I hope that makes sense. Now we'll look at some questions. Of the products formed in the following addition reaction, which one is kinetic and which one is thermodynamic? And what is the major product of this reaction? Through all the reactions that we cover in organic chemistry, you may have noticed that very few of them involve forming carbon-carbon bonds. Why? Because, frankly, carbon-carbon bonds are often difficult to form. The reaction I'm about to teach you, called the Diels-Alder reaction, is an extremely useful way of forming two new carbon-carbon bonds in a single transformation. To summarize, in a Diels-Alder reaction, a conjugated diene, like this one, interacts with an alkene, which we call a dienophile in a Diels-Alder reaction, to make a cyclohexene, like the one shown here. I'll now explain this reaction's mechanism, just so you know how this transformation actually occurs. During this reaction, our diene and our alkene, which we call a dienophile in a Diels-Alder reaction, get close enough to each other that their pi electrons rearrange. That happens like this. And you can essentially think of it as being like the opening and closing of 3 doors on 3 separate hinges. Thus, these pi electrons, if you think of them as being a door attached to a hinge right at this carbon, swing out and close right here, forming a single bond between these 2 carbons. This door, with a hinge right here, swings over here to form a double bond between these 2 carbons. And this door, with a hinge right here, swings out and forms a single bond between these 2 carbons. As that occurs, it forms this product, which when redrawn in a prettier manner is this cyclohexene. There's a tremendous amount of variety that one can incorporate into the Diels-Alder reaction. For example, if we use an alkyne as a dienophile instead of an alkene, then these electrons will do the Diels-Alder rearrangement. Once again, we see the door flip on a hinge right here, this one flip down here, and that one flip here, to form this type of product, which is a cyclohexadiene. There are 2 carbon-carbon double bonds in this ring. Now similarly, we aren't limited to using unsubstituted dienes or dienophiles. Hence, we can begin with a diene and a dienophile that have a variety of different substituents, represented generically here as R1, R2, R3, and R4, to give multi-substituted cyclohexene or cyclohexadiene products. Alternatively, if we use a diene and a dienophile whose pi electrons are already pre-embedded in cyclic molecules, as in this example, then after the Diels-Alder reaction occurs, we can get a polycyclic product. Once again, we could imagine any of these starting materials already being substituted in a variety of manners, which would allow a wide variety of substitution in our final product. Here are several examples of different Diels-Alder reactions that we might do. If, for example, I reacted with my 1,3-butadiene with this compound called maleic anhydride, I would get this polycyclic product. This is a reaction that my organic chemistry students actually do in their organic chemistry lab. Similarly, I could react dienes with an alkyne, as in this example, to get this product, or with a cyclic diene itself to give this intermediate. If this intermediate, which is also an alkene, could then behave as a dienophile in a subsequent Diels-Alder reaction, we can get this tricyclic product. Now, since its discovery in the late 1920s, the Diels-Alder reaction has probably been used to synthesize literally tens of thousands of molecules. Here's one example I thought I'd show you from Professor E.J. Corey's group at Harvard, which in 2004 reported treating molecule 6, called Danes diene, with dienophile 7 and chiral catalyst 8, to stereoselectively give product 9, with 94% enantiomeric excess and 92% yield. Over various other steps shown here, compound 9 was successfully converted into this final molecule known as estrone in enantiopure form. Estrone is an estrogenic hormone of significance in numerous biological processes in females particularly, with specific relation to menopause. Diels-Alder reactions of cyclic dienes give particularly interesting products. For example, if we take cyclopentadiene right here and treat it with this dienophile, then, like all of our Diels-Alder reactions, these electrons flip out here, forming a bond with carbon 1. These electrons swing over here to form a carbon-carbon double bond between 2 and 3, and these electrons flip out here to form a carbon single bond between here and carbon 4. That ultimately provides this product. Now, one thing you should notice is where the atoms in our cyclopentadiene starting material end up in our final product. I've numbered those atoms in both the starting material and the product in this slide for your reference. You can see in particular that atom 5 right here ends up right here in the product, which is pointing towards us three-dimensionally on this slide. This is a little easier to see if we redraw the molecule to look like this. As you can see, carbon 5 ends up pointing up like this. This type of carbon in this unusual spirocyclic compound is known as a bridgehead carbon because it kind of looks like a little bridge between carbons 1 and 4. Now, one thing that you should notice is that I've neglected to show how the stereochemistry ends up being at this position over here. Does the bond to our methyl ester right here end up going up or down in the product? In other words, should I draw this bond as being a wedge or a dash? The answer is both. In other words, we end up forming some of this product in which the ester is pointing down, and some of this product in which it's pointing up. The product to the left is the major product, being formed in 74% yield, while the one at right is the minor product being formed in 26% yield. And just so you know, the product at left is called the endo product, and the one at right is called the exo product. So let's get to some problems. Foremost, I want you to identify the products of the following Diels-Alder reactions. And next, I want you to identify the diene and the dienophile that you would need to assemble this Diels-Alder product. Here are a few additional cool examples I wanted to show you of Diels-Alder reactions. Imagine this molecule, butadiene, reacting with this molecule. You can once again picture the electron swinging like a door on a hinge out here to form a carbon-carbon bond, these swinging this way and these swinging this way to give us this product. And this reaction, as it turns out, occurs even below typical room temperature at 20 degrees Celsius. How about this example? You can actually take an alkyne and do a Diels-Alder reaction. One of the two pi bonds swings out, forming a bond between this carbon and this carbon. These pi electrons swing down to form a carbon-carbon double bond, and these pi electrons swing out like a door on a hinge, forming a bond between this carbon and this carbon. Because this is a triple bond and it's only swinging out one of its two pi electron sets, it retains a double bond configuration in the product. And here's another example. If I take butadiene and react it with this molecule, which actually has two alkenes in it, I can get a Diels-Alder reaction occurring on the left side to give me this product. And then if I introduce an excess amount of my butadiene, it will do a second Diels-Alder reaction to the right side of this intermediate to give me this final product. So now we come to this final subject, predicting the product. If we look at a situation in which I react this diene with this dienophile, we could imagine it doing a Diels-Alder reaction to give the predicted product. However, this diene over here is not a symmetrical diene like butadiene. And what I mean by that is this. You could imagine this diene potentially forming a bond with this alkene, as shown here, or if it approached the alkene upside down, it could potentially undergo a Diels-Alder reaction in this way. If you draw it out on paper, the orientation of this diene, facing up or facing upside down, actually will give you completely different products. So the question is, which of those products actually forms, and how in the world can you predict it? The way we predict it is by drawing resonance structures. I hope you guys can see from the principles outlined in our earlier lecture on resonance structures that you can take the lone pairs on this oxygen and push them down here, simultaneously swinging these pi electrons like a door on a hinge out there to form a carbon-carbon double bond, and pushing these pi electrons out onto this carbon. That gives you this resonance structure right here that has a formal positive charge on this oxygen and a formal negative charge on this carbon. You'll notice that I can't do any real significant resonance structure in reverse, giving a partial positive charge on this bottom carbon. Separately, I can draw a resonance structure of this molecule, in which I imagine these electrons swinging up like this, just like a door on a hinge, to form a carbon-carbon double bond here, while simultaneously pushing these pi electrons up onto this oxygen, giving it a negative charge, as shown here. Contrasting the previous example, I can't show a real significant resonance contributor in which I end up getting a negative charge on this carbon down here. Thus, having this carbon-carbon double bond conjugated to this carbon-oxygen double bond produces a partial positive charge on this carbon at this position. Now, I want you to look at these two molecules and try to imagine how in the world would they get together. Well, if you understand the basic principle that opposites attract, that is, a carbon that has a partial negative charge on it is going to feel an attraction to a carbon that has a partial positive charge on it, you can see clearly that this carbon and this carbon are going to line up. I want you to contrast that with our examples shown over here to the right. I draw the same resonance structures and try to orient them in the opposite direction. Is this carbon right here going to orient with the carbon that has a partial positive charge? Is this carbon with the negative charge going to orient itself to match up with the carbon up here? The answer is no. Over here I'm going to see the partially negatively charged carbon lining up once again with the partially positively charged carbon. I determined their partial charges all by drawing resonance structures. We can see that summarized here. Once again, from our resonance structures, we saw that this bottommost carbon has a partial negative charge on this diene, and this bottommost carbon on the dienophile has a partial positive charge. Thus, this is the way these two molecules are actually going to line up when they undergo a Diels-Alder reaction, thereby giving me this product as the major Diels-Alder product. So that brings us to the end of this lecture. I hope you've had an enjoyable time. I know I have. Feel free to take a break, rest up, get a snack, and then come back, energized and enthused, ready to learn about Chapter 8's coverage of whatever Chapter 8 covers. Until then, have an enjoyable rest of your day.